Imagine standing on a surface where the temperature sits around 465 degrees Celsius. That is hot enough to melt solid lead. The atmospheric pressure crushing down on you is equivalent to diving 900 meters beneath the ocean. And it's raining sulfuric acid. This is Venus. For a long stretch of history, early astronomers peered at those dense golden clouds and assumed there was a lush, tropical jungle world underneath them. They made that assumption because Venus and Earth are essentially twins. They formed from the exact same protoplanetary disk at roughly the same time, using the same mix of rock and metal. Venus is even about 95% of Earth's diameter. With identical starting conditions, sitting in a similar zone of the solar system, these two worlds should be almost indistinguishable. Instead, Earth built a stable climate thermostat and kept its oceans, while Venus became an environmental catastrophe. The physical mechanism that split these two planets onto radically different paths is a specific, measurable threshold. Once a planet crosses it, the rules of its climate change, and the door back closes permanently. To see how a planet breaks, you have to look at how it works normally. Every rocky planet with an atmosphere runs a basic greenhouse effect. Sunlight passes through, warms the surface, and the surface radiates that heat back as infrared energy. When the surface gets warmer, it radiates more energy outward, balancing the incoming sunlight at a comfortable, self-correcting equilibrium. In 1969, Planetary scientist Andrew Ingersoll rigorously mapped out what happens when that balance fails. This flowchart illustrates his concept, known as the Runaway greenhouse effect. As a planet warms, ocean water evaporates. Water vapor is an incredibly potent greenhouse gas, so more evaporation traps more heat, which drives even more evaporation. This feedback loop has a structural limit. As water vapor concentration keeps climbing, it saturates the upper atmosphere. This creates a fixed altitude where the atmosphere physically cannot increase how much energy it emits outward into space. It creates a hard, mathematical ceiling on the planet's cooling system. If the amount of incoming sunlight exceeds that hard ceiling, there is no equilibrium left to find. The planet is taking in more heat than it can physically expel, so the surface temperature climbs endlessly until every drop of ocean water has boiled into the sky. The Runaway greenhouse effect represents the absolute mechanical failure of a planet's ability to balance its energy budget. The physics of that hard ceiling are well established, but planetary scientists do not actually agree on how or when Venus hit it. The longest-standing view is that early Venus had temperate oceans for hundreds of millions, maybe billions of years. In this timeline, the young sun was dimmer, keeping Venus safe. But as the sun gradually brightened over eons, the incoming radiation slowly crept past the ceiling, and the oceans boiled away. A competing reconstruction argues Venus never had a long-lived ocean at all. Because it sits slightly closer to the sun, this theory suggests Venus never cooled enough after formation for water to condense out of its steam atmosphere. It was doomed from day one. And a third pathway suggests Venus was perfectly stable until a period of intense planet-wide volcanism. In a relatively short geologic span, massive eruptions pumped enormous volumes of greenhouse gases into the air, forcing an already warm planet decisively past the threshold. There is no single confirmed villain here. Whether it was slow solar brightening, immediate orbital GIM, or a volcanic surge, all three pathways are actively defended in planetary science literature today. If an episodic event like a volcanic surge pushed Venus over the edge, you might wonder why the planet didn't just cool back down and condense its oceans once the eruption stopped. This atmospheric diagram shows what happens next. Once a planet's entire ocean is in the atmosphere as a gas, intense ultraviolet radiation from the sun bombards those water molecules, breaking them apart into oxygen and hydrogen. Because hydrogen is light, it escapes the planet's gravity completely. That water is gone. This triggers a second failure, shutting down the carbon-silicate cycle. Without liquid water, there is no rain to lock carbon into rock. It simply builds up forever. Crossing the threshold physically disintegrated the water reservoir and disabled the carbon cycle, permanently destroying the exact systems needed to ever repair the climate. Because Venus is the clearest natural laboratory for this threshold, astronomers actively use it today. It sets the baseline for the inner edge of a star's habitable zone when they are hunting for liquid water on newly discovered exoplanets. It also comes up constantly when discussing our own climate, often with the suggestion that human-caused carbon dioxide emissions could trigger a Venus-style runaway on Earth. Current physics tells us that is not going to happen. The scientific consensus is clear. Earth's massive ocean volume and the Sun's current energy output make this runaway threshold physically impossible for humans to reach. The Sun simply isn't hot enough yet, and won't be for hundreds of millions of years. Venus is a lesson in how physical systems behave. Just like the collapsing white dwarf star we looked at in yesterday's episode, a planet's atmosphere can maintain its state right up until it hits a strict, measurable ceiling. Tomorrow, we are leaving the solar system behind and heading to the bottom of the ocean for day 143. We'll look at the reef that can't grow back, shifting from the physics of dying planets to the biological tipping points right here on Earth.
Thank you for sharing this moment of pure wonder. You are the true magic that fuels this journey. Until next time, remember to shine bright.